So I'm going to dedicate this hour to another brilliant kind of fault attack called the Boneh DeMillo Lipton. It's a paper from Eurocrypt 1997. And this attack, I'm going to show you a very nice way in which it was actually executed. And I'm going to you need to remember how it works, because if by some miraculous reason we have enough time for Plunder Vault in next hour, we're going to see how it's being run in a very, very unrelated context. So, yeah, the cat is here. Because you see the sun? There's sun on the cat. Yeah. So, what is the idea of Boneh DeMillo Lipton? What is the idea? So we have RSA operation, RSA encryption, decryption of something. And again, the idea is that the secret key is used for the decryption or the signing, and the public key is used for the encryption or the verification. And as it happens, decryption or signing is quite expensive. And the operation is C to the power of D. You take the ciphertext and you raise it to the power of D, which is equal to M to the power of E, because the ciphertext is a message to the power of the encryption key, M to the power of E times D, and E times D is 1 modulo phi of N, which phi of N is a secret. It's one of the secret key, and then you get M. Right? Does anybody know why is encryption cheaper than decryption? Because it's basically modular exponentiation. Does anybody know? Yeah, okay. Yeah. Well, E is, you can choose E in a way which makes it faster. But this is a very, very expensive operation. We talked about it in class, about various ways of speeding it up. For example, Montgomery. And so this operation is hard, and we want to do a lot of these encryptions. So one very, very classical way of speeding this is using the Chinese remainder theorem. So who here has learned about the Chinese remainder theorem in some other course? Anybody learned about CRT in some other course? So I'm happy that 11 of you are still functional enough to answer the polls. So what is the Chinese remainder theorem? I'll tell you, but first of all, let's do some warm-up. So we have a prime P, a prime Q, and N, which is the multiple of P times Q, which is a composite number, not a prime. And now I want to ask you, let's do the warm-up. So if X is equal to Y modulo N, X and Y are just, numbers. Does X equal to Y modulo P? Yes or no? If X is equal to Y modulo N, does X equal to Y modulo P? So the correct answer is yes. The correct answer is yes. What does X equal to Y modulo N mean mathematically? It means that X is equal to Y plus something times N. Okay, so this means, let's draw it. So let's do, this means that X is equal to Y plus, some kind of, guess what is, if X is equal to Y modulo N, it means that X is Y plus W times N. And N is P times Q. So if X is equal to Y modulo N, then X is equal to Y modulo P, because this is exactly, this is equal to Y plus W times P times Q. Yeah. So the answer is, if X is equal to Y modulo N, then X is equal to Y modulo P. Okay, what about the other way around? If X is equal to Y modulo P, Does it mean that x is equal to y modulo n? Does it necessarily mean? Okay, if x is y equal to modulo p, does it mean that x is equal to y modulo n? And the correct answer is, of course, no. The correct answer is no, because if x is equal to y modulo p, it means that x is equal to y plus w times p, but it doesn't necessarily mean that it's p times q. And if w is a multiple of q, then fine, but it could definitely be the case that x is equal to y modulo p, and it is not equal to y modulo n. Third question. If x is equal to 0 modulo p, does it mean that x is equal to 0 modulo n, necessarily? If x is equal to 0 modulo p, does it mean that x is equal to 0 modulo n? Yes or no? Well, the correct answer in this case is no. Here is an example. What if, I'll just write it down. What if x is equal to p? Look at this. If x is equal to p, then what is x modulo p? It's 0, right? Because p modulo p is 0. But we know that p and q are prime numbers, right? So it can't be that p is a multiple of q, because p and q are primes. Yes, of course, it's a special case, but so what? I didn't say it's a hard question, right? So if x is equal to 0, it doesn't necessarily mean that x is equal to 0 modulo n. Just for the people at home, let me just write down which one of these are wrong, okay? So if x is equal to y modulo n, then x is equal to y modulo p. If x is equal to y, it does not mean, not necessarily. And if x is 0, then does not necessarily. So now please answer in the chat, how much is n modulo p? What is n modulo p? So n modulo p is indeed 0, because n is p times q, which is a multiple of p. So the answer is 0. And how much is x times p modulo p? What is the answer? The answer again is 0, because x times p is a multiple of p. Awesome. So now we are ready to talk about the Chinese remainder theorem, as you've never seen it before. Right. So here is the Chinese remainder theorem. One year, maybe next year, I will have time to prepare for the course more seriously, and I'll learn how to pronounce this in Chinese. All I can say is that the guy who wrote it was called Sun Tzu Xuanqing. It was in the 5th century, and this means Sun Tzu is the teacher Tzu, I hope, or maybe it's a teacher Tzu. I think it's a teacher Tzu, and it's not the same guy who wrote The Art of War. His name was also Sun. Sun Tzu is like Professor Cohen. Could be plenty of people who do that. And this is this is like a book of riddles, and here is one of the riddles. The riddle is, there are certain things whose number is unknown. If we count them by 3, you see the 3s? Isn't that cool? If we count them by 3s, we have 2 left over. If we count them by 5s, we have 3 left over. And if we count them by 7s, we have 2 left over. How many things are there? How many things are there? No? So what is saying 21? Remember, you understand the question. So I have a bunch of Chinese soldiers, and I'm trying to get them arranged before the parade. And I tell them, arrange yourself by 3s. And it doesn't work out really well. It can't be 21 OL, seriously. 21 modulo 7 is 0. It's 23. Yeah, 23. If I arrange them by 3s, I have 2 left over. Okay, I'm telling the soldiers, no, let's try another arrangement. Arrange them by 5s. Doesn't work. We have 3 left over. Arrange them by 7s, and 2 left over. Then the answer again is 23. So what the Chinese remainder theorem very hand-wavingly stated, says is that if you can solve an equation modulo some prime factors, you can also get the unique solution modulo the multiple of these factors. And this is not a math course, so I'm not going to give you the exact equation. But what the meaning of this is that I have an operation I want to do modulo n, and it's very expensive to do it modulo n. I am going to find the solution to this equation modulo p, and I'm going to find the solution modulo q, and then I'm going to do a Chinese remainder step, which I'll just show you. And I will get a unique answer. So there's a unique solution. If I found the solution modulo p, and I find the solution modulo q, I found the unique solution modulo n. And let's see how we do it in RSA decryption. So again, my objective is to calculate c to the power of d. This is my decryption operation. And if I do it modulo n, it's going to be very expensive. So the first thing I do is do c to the power of d modulo n, but I'm going to do it modulo p. How do I do it? I'm going to take c and reduce it modulo p. And then I'm going to raise it to the power of d. So reduction it's not so expensive. It's not so cheap. I have to do one reduction. And then my exponentiations are modulo p. And now my result is going to be some kind of number c to the power of d modulo p. And this number is not equal to c to the power of d modulo n. For starters, it has to be between 0 and p. And c to the power of d modulo n is between 0 and n, which is a much larger number. So this is one number. This is m sub p. And also I do this again. I do it m sub q. So now I have c to the power of d modulo p and c to the power of d modulo q. Each one of these operations took me 1/4 of the time to calculate compared to c to the power of d modulo n. And this is because multiplication is quadratic in the length. So it doesn't matter how I did the multiplication, Montgomery, not Montgomery, sliding window, not sliding window. It took me 1/4 of the time to calculate to calculate m sub p and m sub q. So in total, I paid 1/4 of the time to get this, and 1/4 of the time to get this. Great. And by the Chinese remainder theorem, I know that there is a unique m such that m modulo p is m sub p, and m modulo q is m sub q. And all I need to do now is combine these two values somehow to get this m, this big M, which is a number between 0 and n. How do I do that? I just open my handbook and I see how is this Chinese remainder theorem implemented. I look at my handbook of applied cryptography, and this is the equation which is written there. So CRT of m sub p and m sub q is m sub p times q times this number, q minus 1 modulo p, plus m sub q times p times p minus 1 modulo q. So what is this number? Q minus 1 modulo p. This is a special number which exists by the definition of the prime group. If I multiply q minus 1 by q, what do I get? 1, but only if I do it modulo p. Yeah, I get 1 modulo p. Thank you. It doesn't work over modulo n, for example. So let's just make sure that this works for us. So I'm claiming that this thing, modulo p, is equal to m sub p, and this thing, modulo q, is equal to m sub q. By the way, how do I get this number? I can use extended GCD, but I just know that it exists. Don't worry, it exists. Okay. So let's check that m modulo p gives me m sub p. So there are two parts to this value. This is m sub p times something, and m sub q times something. So I'm going to take m and reduce it modulo p. Great. So what is m sub p modulo p? It's m sub p. Great. What is q modulo p? Some common number. Q modulo p. Yeah, doesn't have any special meaning. What is q modulo p times q minus 1 modulo p? 1 modulo p. Okay, so this thing is m sub p times 1 modulo p. What about this? Look at this side. So this is p times something. I don't know what is this other thing. So p times something modulo p is always what? 0. Remember from the previous slide? P times anything modulo p is 0. So as soon as I do modulo p, this part falls away, and I remain with m sub p times 1 modulo p. And if I do reduction modulo q, then this multiplication by q kills this part of the equation, and I'm left with m sub q times 1 modulo q. So who wants me to convince them again that if I take this and reduce it modulo p, I get m sub p? Who wants me to explain why m modulo p is equal to m sub p? Who wants me to explain again? Okay, I'm happy to explain again. No problem. So this m, p and q, do they have to be co-prime? Listen, this isn't. I didn't prepare this well enough to answer. I'm sorry. Maybe somebody in the chat. There's a cryptographer in the chat. Can answer you. I don't know. I'm sorry. I don't want to tell you something wrong. So I want to show you that if I take m and reduce it modulo p, I get m sub p. So there are two parts to this term. There is the left part, which is m sub p times something, and there is the right part, which is m sub q times something. When I reduce it modulo p, I'm going to get this thing modulo p plus this thing modulo p. So m sub p. Let's deal with the right part first. So anything multiplied by p modulo p becomes 0. So as soon as I do modulo p, this right part becomes 0, falls away, because it's multiplied by p here. P times x modulo p is always 0. Now the left part has m sub p times q times the inverse of q. Now the inverse of q is defined. We defined it that if I multiply q by the inverse of q, I get 1. So this part becomes 0. No. I'm showing you that if I reduce this modulo p, I'm going to get m sub p. Okay? I reduce this modulo p. So this is the Chinese remainder theorem. I showed you that using this trick, I can get a value which is equal to m sub p modulo p and m sub q modulo q. And by the definition of the Chinese remainder theorem, this is the unique answer to c to the power of d, which is lovely because this again took me half the time to calculate. So all of these operations were fast. Can I do another? Can I do this again? Maybe I can split p into 2 parts and do like p1 and p2. Is there a way? Yeah, OL caught the problem. So I cannot reduce this again because p is prime. You can't split it into 2 composites because that's the definition of a prime. You can't factor it, right? So I can only do it once, but still saving half the time. Everybody does it. Yeah, one thing doesn't really help me. Yeah. You can do it. In your startup, you will do it, and you will put it on your white paper that you use double Chinese remainder theorem.